question that we had. We started this like, I don't know, 7, 8 years ago. It's already been a long time. About semitoric systems, which you've heard of in the previous talk. And more precisely about constructing explicit semitoric systems starting from some part of their symplectic invariance. So there will still be some things that Joey didn't talk about or briefly evocated that I will have to review, which is like what are semitoric systems, he said, but what are the symplectic invariants, and in particular those we want to keep among these invariants. And then I will be in a good shape to tell you which was the question that we had. It's very general and somehow very naive. But we were young and naive at the time. We're still naive, maybe. But still it was naive, but we managed to derive some very interesting results by using this naive question, taking a naive approach to it. And I will explain this in the first part of my talk. And then the next part will be about some paper we are finishing writing now among the 10,000 papers Joey is writing with everybody. And which discusses the limitations of the naive ideas we had to solve for general question. But or you can adapt what we did in the previous paper to overcome this. So this is like a standard outline of any mathematics talk, I guess. But let me enter into detail. So, okay, I can go quickly on that. So everybody knows what an integrable system is. I just want to emphasize that. Like in Joey's talk, it will be always in dimension 4, so a 4-dimensional compact symplectic manifold. And I will have an integrable system, so the data of two Poisson converting functions whose differentials are almost everywhere linearly independent. And okay, Joey also talked about Arnold-Liouville-Miner theorem that everybody probably knows. If you assume that the fibers are connected and you look at the regular value of the momentum map, then you know that you have semi-local normal form in the neighborhood of the corresponding fiber. Which tells you that a neighborhood of this fiber is locally symplectomorphic to a neighborhood of the zero section in the cotangent bundle of the two torus, and that you can bring the momentum map up to composing with some diffeomorphism to the momentum map for some very nice dynamics in the cotangent bundle of the torus. And this momentum map is called action variables, action coordinates, and in particular, it's the momentum map for, it's a local toric momentum map. It's a momentum map for a local toric, a local T2 action, effective T2 action. And we've been hearing about toric systems in Joey's talk as well. But I just want to remind you that for toric manifolds, as Joey said, everything is encoded in the Delson polygon. So I'm talking about dimension 4 again only. This polygon is the image of the momentum map, so it's a result by Atiyah, Gaimin, and Sternberg that it's a convex polygon. And Delson showed that this cannot be any polygon. There are some conditions. In dimension 4, the only condition is that at each vertex, you look at the emanating edges, and they are spanned by the basis of the 2. And moreover, what he showed also is that this polygon completely determines the system after equivalent symplectomorphism. So it means that you are equivalently symplectomorphic if and only if you have the same polygon. But also, so something I want to insist on today is that if you give me a polygon, and I have Delson's paper or some lecture notes with me, I can look at the algorithm, which gives me from this polygon a representative of the isomorphism class. So a toric system with this polygon as its momentum map image. And not only the algorithm explicit and doable by anyone, it's really simple, but also the outcome is explicit. So in the end, you get the manifold, the symplectic manifold, as a symplectic reduction of some power of C by some Hamiltonian torus action, and the action is explicit. You have the explicit generator of the action. Okay. Now I want to go to semitoric systems. And we've heard about them already, but I want to talk a bit about singularities because we'll see some of them later in the talk. So as Joey explained, if you look at a toric system, you look at the momentum map image, the polygon. So in the interior of the polygon, you have the regular values, the fibers are tori. In the interior of the edges, you have one tori as fibers, and vertices correspond to fixed points of the titration. So these singularities are what are called singularities of elliptic something type. I shouldn't have put this slide in the talk, I guess, so don't look at it. Okay, there's a good notion of non-degenerate singularities that Joey cleverly didn't define and that I don't want to define as well. But the point is that when you have this good notion of non-degenerate singularity, then you have a nice symplectic normal form near every singular point. Namely, your singular foliation is given by two functions Q1 and Q2 that have to be taken in this list. And the first items, you recognize them. If you have, instead of being in dimension 4, you want a surface with a Morse function, these are the regular points, the elliptic points and the hyperbolic points. So you already have seen these people. And in dimension 4, you have another type of singularity that we already saw as well, the focus-focus singularity. And as Joey said, one of these two Q1, Q2s that come together when you have a focus-focus singularity generates S1 action. This theorem, due to Eliasson and building on the work of many people, I guess, is a bit better, much better when you don't have any hyperbolic singularities. You have directly that your momentum map is exactly Q and Q2 up to some diffeomorphism. So in semitoric systems, so again, this is the same definition that Joey showed. You will not have an effective Hamiltonian T2 action, but you will have an effective Hamiltonian S1 action generated by the first component. And if you do this and you allow any h such that jh is integrable, well, you can have maybe degenerate singularities, and we don't like that, so don't allow degenerate singularities. But even if they are non-degenerate, you could have hyperbolic singularities, as Joey explained. You can have hypersemitoric, well, in hypersemitoric systems, you also have one kind of degenerate singularities, but who knows. So you forbid all that. So you have that the singularities are non-degenerate and no non-hyperbolic. And as Joey said, the image of the momentum map looks like that. You still have the elliptic something singularities on the boundary. You still have the set of regular values inside the image of the momentum map, except that for some isolated points here, these correspond to focus-focus values. And the corresponding fiber, as we saw, is torus pinched at one or several focus-focus points. And the pinches correspond to focus-focus. We need non-simple systems in what we do, but for today we won't care. I will talk about simple system. What does it mean? It means that the tori corresponding to focus-focus fibers will only be pinched at one point and not several ones. And moreover, each time you look at the image of the momentum map and you take a vertical line, there will be only one focus-focus value in this line. Okay, this slide is more risky than anything because if I have forgotten anybody, I won't go out alive, I guess, but it's just to tell you that these systems have been interesting for a lot of people. As Joey said, these are kind of almost toric vibration as Milton in O3 and the definition that I just showed you with Newton in 7. Okay. And here are some historical examples that in fact predated the definition of semitoric systems. And that were coming from physical models that were very simple. So one of them is obtained by coupling classical spins in a non-trivial way. And here the effective Hamiltonian S1 action you consider is you have two copies of the unit sphere. And you rotate about the two vertical axes at the same time. Okay? And you can cook up some Hamiltonian H, so that the corresponding system is semitoric. Here is the image of the momentum map. It's the interior of all of these red lines. And there is one focus point, and the corresponding value is this black circle. And we'll come back to this example later, but I also wanted to tell you that this exists in the non-compact case, but I won't talk about the non-compact case today. But it's also one of the motivating examples. It's not far from this one. And in the non-compact case, you have the additional property in the definition that you want J to be proper to be able to perform some more theory for J. And I mean, my goal will be to talk about additional explicit examples. I've put some names here. Again, I probably forgotten some names, but anyway, I will be talking into more details about all these examples later. Okay, and this will be the technical part, and then I will ask the main question that we have. And then there will be pictures until the end. So, stay with me for 5 minutes, I guess. I want to tell you a bit about the symplectic invariance of semitoric systems. So a lot of you already know, but for those who don't know. So there's a classification, a complete classification due to San and Alvaro Pelayo about 15 years ago. And it's based on a certain number of invariants that are not independent, but for the sake of the presentation, it's easier to say 5 invariants. So there's a good notion first of isomorphism, which is exactly what you would cook up if I asked you to come up with a notion of isomorphism. So you want a global symplectomorphism, sending your momentum map to the original one composed with some diffeomorphism. But remember that the first component of the momentum map is special. It's the one generating the S1 action. So this diffeomorphism has to preserve the first component. And then you have some question of orientation that simplifies a little bit the classification, but you shouldn't care. Okay, and something that I forgot to tell you because I'm bad is that a toric system is certainly an example of semitoric system, but with zero focus singularity. Okay? And a T2 equivariant symplectomorphism is certainly an example of such an isomorphism. So, okay, and toric systems are classified by their Delson polygon. So certainly in the list of invariants there should be a complex polygon somewhere. So this is the first invariant. The other invariants are a certain number of marked points in the polygon. And these come from the various focus values of the system. And for each of these points you have 3 quantities. Okay, if you say it's a marked point, you already know the first one, which is the 8th of the point in the polygon. And the other ones, I will not use them, but so I will not say much about them, but one of them is a formal series in 2 variables describing the local singular dynamics near the singularity. And the other one is an integer, which describes also some local momentum map sits with respect to some global momentum map used to construct the polygon. which I will tell you about in 1 minute. But again, we won't care about 3.2 and 3.1. And then something that I have to be careful when I say it is that there's an explicit construction. So the result of San and Alvaro is that you're isomorphic if and only if you have the same invariance. Moreover, if you give me a list of invariants, I can construct a semitoric system with these invariants. The construction is totally explicit. You can open the paper, you have semi-local models near the elliptic something singularities, near the focus-focus singularities, and in the regular parts. And using the invariants, you have a recipe on how to glue these semi-local models symplectically. But the outcome, certainly, you're doing symplectic gluing of several different normal forms, and the outcome will not be something completely explicit. What do I mean by that is that, again, in Delzon's algorithm, what the outcome is you have explicitly the manifold in terms of the symplectic reduction by some explicit T2 action, and you have explicitly the Hamiltonians. And so this is what motivated us. We were thinking, okay, we like explicit examples. We like Delzon's construction. Can we try to do the same, maybe at the price of forgetting some of the invariants? And again, forgetting some of the invariants means we will forget the twisting number and the Taylor series. So I need to tell you a bit, and this is, I promise, the end of the technical part, but I need to tell you a bit about how we construct these invariants. So these three invariants are combined together in what is called the Mark semitoric polygon. Okay, so as Joey told you, this polygon will encode the singular integral affine structure of the manifold of the system. So what does it mean? It means that what is the integral affine structure if you have a toric system? It's like you have a toric momentum map. These are global action variables, and this is it. The image is a polygon. Okay. So we should try to mimic the same thing, and let's try to have some toric momentum map defined everywhere, and then the image will be a polygon, and we'll be happy. Of course we can't, because there's a singularity somewhere in the middle, and there may be several focus-focus singularities, but I was too lazy to draw them. Okay, there was no room on the slide. But then, okay, let's try to be stupid. So let's start at some regular value. Take some action variables near near the corresponding fiber. And we already have one action, which is J. Okay, so take these action variables of the form J something. And then try to extend them naively to above every point of the momentum map image. So if you try to extend to the elliptic something singularities using the local normal forms, you can see that this is perfectly doable. So you can extend all the way to this part, and then you will get the image of these semi-global action variables will be a piece of a polygon. But then trouble happens when you want to extend past the singularity. Why? Because if you try to extend past the singularity and you loop around one singularity, you start with action variable jk, you will end up with action variables j plus k. There is some non-trivial monodromy. What is good for you is that actually this monodromy doesn't depend on your system. It only depends on the number of points of focus values encircled by your loop. So it's 1, so there's a 1 here, but if you add k points inside your loop, you will have a k. So then what you do is that, okay, let's make the set of regular values simply connected by cutting somewhere above or below the singularity. And if I cut above, then I will try to extend by going below and extend all this way and all this way. And everywhere but on the cut, I will have a toric momentum map. But then I want to glue back to some momentum map which will not be toric anymore along the cut. or the several cuts if you have several points. And then using this form of the monodromy, you have a recipe on how to glue, and you can construct global momentum map which is not toric but whose image is a convex polygon, and you get the polygon like this. And then you have the mark points that are the images by these maps of the, okay, I've talked about one map here, still only. So you have this map, and then you look at the image of the singularity by this map, and it will give you the mark point, and if you have several singularities, you do the same, you have several mark points. And then the 8, again, it's just the 8 in the polygon, which, by the way, has a geometric interpretation. It's a symplectic volume of some manifold, but we don't care. But we also have choices. The choices are the following. So here I've done, I've explained what happens when you cut up. So this gives this polygon, but of course you can cut down. This gives this other polygon. And if you have several points, each time you have 1 point, you have 2 options. So this multiplies the number of polygons you get. But also there's something else, which is we started with some action variables of the form J something. But you can take other action variables of the form J something else. And the freedom is in the choice of the second variable translated into the action of these affine maps on the final polygon. So you have an infinite number of polygons. Okay. Okay. So again, the main question we had was the following. So we give the mark semitoric polygon. This is invariant. Now, can we construct a fully explicit system, again with fully explicit manifold and fully explicit Hamiltonians, having this as its invariance. So of course, I mean, it's not unique. I mean, you have many non-isomorphic semitoric systems which will have the same mark semitoric polygon because we are forgetting the other two invariants. Okay? But still, can we construct one of them that is fully explicit and nice? I want to insist on something which is a bit stupid, but still I need to insist on it because I will show you some formulas and there will be a lot of parameters in the formulas. And don't be afraid, there are some good reasons. One of the reasons is that, again, I didn't have time to specify the coordinates of the vertices of the polygon here. But I mean, I'm not only interested in the shape, right? I'm interested in the precise scalings of the polygon. Okay? This will induce that I will have some parameters that I need to take into account in my explicit systems. And also, again, the mark semitoric polygons, there's the data of the 8 inside. Where are these mark points vertically? And I mean, I want to be able to, okay, take this one, but also take the same polygon, but this mark point, instead of being at this 8, it's at this 8. So I want also to keep track of this. And to do so, we will have to have many parameters. And this will lead to ugly formulas, but whatever. Is the main question clear, or is everybody already asleep? Okay. So John at least is awake. Thank you. Okay. So, for the next half of the talk, I will tell you first about what we did in an earlier paper. We had a very naive idea, and it worked for some systems, and it was nice, and then we realized later that we were stupid. Okay, maybe I was stupid and Joey was following me. But this couldn't work all the time. There are some very obvious obstructions, and I will explain this in a second part. This is it. But okay, first, this naive idea, what was it? So if you go back to this historical example of coupling two classical spins in a non-trivial way, well, the non-trivial way could be done like in different ways. So these come in a family where J is fixed. It's still the one generating the rotations about the two vertical axes in the two spheres. But H depends on a parameter, T, and it interpolates between Z1, which is just the one generating the rotation in one of the spheres, and the scalar product of the two vectors. And the system that I showed you earlier was the t equals 1/2 system in this family. And if you look at the momentum map image, what's going on is that this is the image for t equals 0. This is the image for t equals 1. So it's obvious on this one, maybe not on this one, but they are not torics, they are of toric type, which means they are semitoric with 0 focus singularities. But then one of the singularities, one of the elliptic singularities, comes inside, undergoes what Joey already told you is called an Hamiltonian of bifurcation, becomes focus for some time, and then becomes elliptic again, and has changed from the top boundary to the bottom boundary, as explained in this Joey's talk as well. Okay, this is nice. So the naive idea we had is, okay, is this behavior universal? I mean, or at least useful to construct as many explicit examples as we want. And so then what do you do if you think this is the case? Then you forget that this system exists, and you look at the polygons. I mean, some representatives of the polygons. And if you look at the simplest that you can come up with, and you took one of these representatives with cut up and one with cut down, and you compare this with the images at t equals 0 and t equals 1, they look suspiciously similar. So then the idea was, okay, so what if I only know these polygons, sorry, and I want to construct an explicit system with these polygons. So I look at them and I realize that if I remove this cut and this point, this is a nice Delson polygon. So I can use Delson's algorithm to construct an explicit toric system with this polygon as its momentum map image. Okay, and this will give me my JH0 in my family that I want to. Okay. I want to do something similar to this. I want to keep a fixed Hamiltonian S1 space M omega J, and I want to change H, and I want to interpolate in the same way. So I would like to find some H0. So I have JH0 by Delson's algorithm applied to this polygon. Okay, and then if you manage to come up with something that allows you to find a good way to obtain H1, a good H1, and you interpolate between H0 and H1 in this way, maybe you will be lucky and you will get your family of systems that in the middle is semitoric with one focus point and exactly this polygon. Okay, is this okay? Yeah. Okay. Again, this is naive. But it worked for some systems. And here is an example on the first Yersborg surface. So if you don't like it or don't know what it is, I mean, there are two answers. The first answer is that if you look at this toric polygon and the natural toric system that you construct from Delson's algorithm, the underlying manifold is the first Yersborg surface. So here the slope is 1. Or otherwise, it's just, you can define it. I mean, you apply Delson's algorithm, it will give you the manifold by an explicit symplectic reduction of C4 by T2 action. And the T2 action is generated by these Hamiltonians. Okay. So whatever, we have an explicit formula for the J and the HTs. Okay, it's ugly, but it's explicit. And the behavior is again the same. You have an elliptic point here, which becomes focus after some time, after undergoing some Hamiltonian bifurcation. Here it's focus, again, and then it becomes elliptic again. Okay, so it worked for this system, and it was nice. And the story about the polygons is the same. These are exactly, if you compare them to the image at T equals 0 and the image at T equals 1, this is what you expect. It's not a coincidence, but I'll tell you more about this. I know, okay, we pushed it a little bit further.
Sorry, can
Yeah.
you come back to the previous example?
Oh yeah, sure.
So the alpha and beta are there for the
Oh,
corners, and what is gamma doing?
Yes. So gamma is in this system expanding the range of time of parameters during which the point is focus. Expanding or diminishing, I don't remember which way it goes, but this is it's fine. And anyway, I mean, no matter what gamma is, the one-half system is always symmetric between focus. And also there are some limitations of gamma. I mean, if you're naive and you don't put a gamma, maybe it's not good enough. Gamma has to be smaller than something for the story to work. So. And yeah, the alpha and beta, actually, you're right, I didn't talk about them, but I mean, they are the scalings of the polygon, so we need alpha and beta if we want to get every polygon of this shape, but with all the possible scalings. So we needed them. And yeah, so what happened is that Joey and Sonia generalized the classical the coupled angular momenta system to a two-parameter family of systems on S2 times S2 with the same behavior as these families that I will tell you about now. And we said, okay, we've constructed this one-parameter family, which is nice on the first Higgsbourg surface. Why not trying to do something similar to them, but on the second Higgsbourg surface, where you have these 2 points that are elliptic and can become focus eventually. So we managed to do it. So you have, if you look at a row or a column, one of the elliptic points is becoming focus at some point, and elliptic again, or this column here if you want. And in the middle, two of them are inside, they are really focus. Okay, and what is nice, but okay, you have the same story about the polygons, and what is nice is that, again, this is completely explicit. And this is very ugly, I agree. I mean, although after seeing just I agree, nothing is ugly anymore, but still it's a very ugly formula, but it's completely explicit. You have, again, the manifold. Explicitly, you have the Hamiltonian explicitly. The Hamiltonian is interpolating between 4 different Hamiltonians, and there are then these 2 parameters, S1, S2, and the endpoint Hamiltonians are ugly, but who cares? They are explicit. So this was nice, but we were, as I explained, much too naive. There are some obstructions to doing this, to performing this story that I said, like trying to fix the Hamiltonian S1 space and come up with a good one-parameter family of HTs, making a point elliptic, focus, and elliptic again. And these obstructions, actually, they are clear once you know what Hamiltonian S1 space is and once you know about the Kershon graph that Joey talked about. But we missed them for some good reason that I will explain later. And what are these obstructions? So, again, we have a fixed Hamiltonian S1 space and we're varying the other Hamiltonian. And as Joey said, some important people in these Hamiltonian S1 spaces are the people with non-trivial isotropy. And the obstructions come from this non-trivial isotropy. Okay, why? First of all, because it was proved by Zung first, I think, that if you look at a focus point, as Joey said, it's a fixed point of the S1 action, and the weights of the S1 action at this point must be -1 and 1. So what does it mean? Near a fixed point of an effective Hamiltonian S1 action, you have a normal form in terms of 2 integers. And these integers are the weights, and they must be -1 and 1 when you are a focus point. But okay, you can be an elliptic point and have weights different from -1, 1. One way to see it is, as Joey said, you can read these things on the mark semitoric polygon. Okay, I've removed the markings because you don't need them in this one. But your elliptic point, the corresponding value, will lie on a vertex of the polygon. And look at the slopes of the edges emanating from this vertex. Here, the slope of this one is 1 over n minus 1, I think, yes. So if n is bigger than something, well, this slope is 1 over something bigger than 2. And this slope, the denominator, will give you the weight of one of the weights of the point. So I don't know, it's n minus 1, or maybe here it's 3, or I don't know which n I put. So the weights of this guy are not plus or minus 1. So this guy can certainly never become focus-focus. Can certainly never enter inside, because it doesn't have a good weight. So weights are a property of the S1 action. So you cannot change them by changing the H. Another obstruction is of a similar flavor, actually. It's these famous ZK spheres that Joey talked about. So, as he said, the ZK spheres, so the spheres of points with isotropy ZK for the Hamiltonian S1 space, in a semitoric system, their image in the momentum map image has to lie on the boundary. And correspondingly, in the semitoric polygon, it has also to lie on the boundary. Okay? So now, what's going on? If we start with this polygon, here there's a Z2 sphere. Why? Again, because the K in the ZK can be read on the polygon. Here, this line in red has slope 1/2, and this corresponds to a Z2 sphere. So if you start to do what we wanted to do, and you start with this point, and it's elliptic, and it's nice, it has a good ways to become focus-focus, so you try to make it enter inside, and you can do it for some time. But then at some point, something should happen, because we said, okay, we want this point to travel to the other boundary, but on the other boundary, there's a Z2 sphere. So something's going on. Either it cannot go to this boundary, and something will happen before, and I don't know what, or it can go to the boundary, but then the Z2 sphere also has to be on the boundary, so the fibers will be disconnected here, something maybe degenerate will happen. I mean, as Joy said, the fibers of a semitoric system are connected anyway. I mean, so who knows what can happen? So this is another obstruction which prevents us from applying our very naive idea of traveling from the top boundary to the bottom boundary and undergoing two Hamiltonian bifurcations. I mean, in this way. So again, as Joey said, everything can be read on the polygon because of the work by Sonia, Silvia Sabatini, and Daniele Sepe, who proved that from the polygon you can read the Kershon graph. And all these things are contained in the Kershon graph, as Joey said. But still, we managed to change a little bit our strategy and to develop exactly these systems. And I think I will have time to explain how we change our strategy right before dinner, but I guess everyone will be tired, so we'll see. Here is a system on CP2, which is completely explicit. Again, the formula is ugly. I will explain it later if I have time, but don't look at it. But everything's explicit again. And again, you start at t=0 with something which is of toric type. You have a nice elliptic point here. It starts entering inside. It does undergo a Hamiltonian bifurcation and becomes focus-focus. So then we have, I mean, we wanted to start with a semitoric system with a polygon corresponding to the one that this system has. So we were happy, and then we could stop here. But then let's see what it does afterwards. Afterwards, what it does is that it keeps staying focus for some time. But then it doesn't go to the other boundary as predicted. It does something else. And what does it do? So you cannot see anything here, I guess. Here it's a bit better, but here you can see there's a triangle attached to the red point. And Joey spoiled my talk because he already told you what is this thing? It's a flap. It's a flap with an elliptic point here and two parabolic points on the other vertices. And I will show you a better picture in one moment.
So sorry, one question. You need these two parameters, gamma and delta, because you want to control the two phenomena. So like,
yes,
push the point inside and make the point become like a.
So it's very interesting actually. If you don't have delta, I mean, okay, I will explain it right now. Okay, so on the system, the Z2 sphere, there's one. Its image in the momentum map image is the bottom boundary all the time. We wanted it to be the bottom boundary or the top boundary all the time because it has to be on the boundary if your system is semitoric. Okay? But in our recipe originally, we had something to come up with, so this is the H1 basically, or the H1 half. We had something to come up with this term, which will ensure that at some point, at equals 1/2, the point will be focus. But then if you only do this is something local near the point, which tells you that it will be focus, and then maybe something bad can happen somewhere else in the manifold. And the point is that if you're unlucky, the Z2 sphere can enter the image of the momentum map, and then you will have degenerate points. So we want it to be on the bottom of the momentum map image all the time. This is what delta does for us. Okay, I know we lost everybody, but thank you, it was a very nice story. And yes, so yeah, Joey already showed you a flap. So this is the same kind of flap he showed you with the fibers that are still here, actually. And something that I should tell you, actually, which is, if I understand correctly, the paper by Holger, Konstantinos, and collaborators, they have a similar system on CP2. I mean, similar but different. But I think what it does in your system is that precisely there's a flap trying to form exactly when the point arrives at the boundary, at the bottom boundary. But you never see the flap because the point arrives, it's degenerate, something happens here. You don't have time for the flap to form. Am I saying something stupid? No. Okay. And I think, I mean, we think, and the point is, you have these bonds on delta and gamma, and if you take the optimal gamma and delta to saturate the inequality we use so that the Z2 sphere arrives at the bottom of the momentum map image, this is exactly what will happen. The point will do the same as in their system. You won't see the flap because at t equals 1, it will arrive here exactly on the Z2 sphere, and so your system is not hypersymmetric, it's whatever, I don't know. But okay, and maybe I should stop soon. So we are very proud because we managed to prove all this. So not only we have the pictures of, yeah, of course it was the same for the other pictures, we proved stuff. We are not doing pictures only in our lives, unfortunately. But we proved all of this, that the system is of toric type whenever you want, semitoric with one focus point with this polygon. And hypersymmetric with one flap, and we said stuff about the flap, we control the size of the flap also in terms of delta and everything. So it's really nice. And by doing this, we obtained all the possible polygons like this. So all the possible sizes alpha, and all the possible 8 invariants, which means that you can make the flap appear as close as you want to the bottom boundary, so you will get arbitrarily high 8 invariants, I guess. Arbitrarily close to the maximum one, or to the minimum one in this case. Okay, why is this interesting? Well, first of all, because we couldn't do anything else first. So previously we had these systems, they had no ZK spheres. And our naive method was working because there was no ZK sphere. And then we realized we were stupid, we should have known that there were ZK spheres sometimes. And we were lost. But then we managed to get something fully explicit for a system with a Z2 sphere. And we were already very happy. But this system also is special. This system is part of the list of the minimal strictly symmetric systems. So what does it mean in 2 minutes, I guess? Toric systems, you may know that if you look at the Delson polygon and you chop off a triangle at one corner, this performs for you a T2 equivalent blow-up in your system, right? Here you have the same. As Joey said, if you take any integrable system and an elliptic point of the system, and you look at the local normal form, it gives you a local toric momentum map. You can perform the corresponding blow-up, and this gives you a blow-up. And if you start with doing this with a system in the semitoric category, you will end up in the semitoric category again. So there are blow-ups of this type, and there is also another kind of blow-up which you cannot see here because it requires a vertical wall, so a fixed surface of the S1 action, as Joey talked about. And it trades you some volume of this vertical wall for a new focus-focus singularity. So these are the systems, the polygons, that cannot be, that generate every other semitoric polygon by performing a sequence of these two types of blow-ups. Or equivalently, somewhat easier, I guess, you look at this list, you can never perform any blow-down to them. And these are the only ones. So this is why they were interesting, and we started looking at them. In the systems that I showed you earlier with the first naive approach we had, and also in the system by Sonia and Joy, you get all the polygons of this type. I showed you the one on CP2, which gets you all the polygons of this type. Also, in Holger and Konstantinos and collaborators' paper, you also get all the polygons of this type. But then you have 3 more types that are a little bit weird. And I guess I will end with this. We struggled, but we managed to get something explicit for each of these 3 weird types. And they are weird also because they have a parameter n inside them. And the one with parameter n has a z n-1 sphere. So we'll have arbitrarily big, z big spheres when you vary n. And you have one extra parameter, but we still manage to get something explicit, which also has the same behavior at some point. It has a flap appearing. And I guess I will stop here and not bother you with the details of the strategy, because everyone is tired. Thank you very much.